All right, common velocities. Okay, that's where our last piece is called common velocities. And by definition, what is common velocity? So when two rotating objects are connected by the same axis, okay, so they're on the same fold, they have the same angular velocity. Make sense? No matter the size, if there are two wheels anchored together, they're going to be moving in that same angular velocity. Make sense? Yes. Okay, yes. Yes, read for us.
When two rotating objects are connected by a belt, chain, rope line, or their edges, they have the same linear velocity.
Okay, so they're going to be moving at the same speed, right? Okay, and that's what we're going to be talking about. So, first example. Did any of y'all ever have big wheels as a kid?
Yes.
Yeah.
I know exactly what you're talking about.
That's a big wheel. One wheel is big, the other two are little.
I had one now, fellas.
I said, and literally said big wheel. No. Yeah. Hot wheels are like tiny cars.
Yeah.
They're not called big wheels. That's just called a car. I know what you're talking about, but they're not big wheels. Big wheel means that you have one big wheel and two little ones.
They just feel like a hole in my wall, and I probably put 100 Hot Wheels.
Yeah, I was like, Hot Wheels, they're my son has a suitcase that says Hot Wheels on it, and it's full of Hot Wheels. All right. Elliot, my little one, he has a big wheel and it's Paw Patrol. And so he it's like yeah. All right. So this crazy car is a child's tricycle with it, and he calls it his tricycle, not a big wheel, which yeah, he calls it a tricycle. Back in my day, they were called big wheels. With a large wheel in the front and two smaller wheels in the back. The front wheel has a diameter of 120 inches. I said 100.
Real mad. Y'all got to do this one day.
20 inches. You're funny. And each of the back wheels has a diameter of 6. Okay, of 6 inches. Okay. As a child drives the crazy car, would the wheels have the same angular or linear velocity?
Yes.
Which one? Which one would they have?
Angular.
Linear. Why would they have the same linear velocity?
Because they're different sizes.
That has nothing to do with it.
Basically, right?
Is it because they're connected?
Because they are connected.
Oh, because they're not on the same axis.
They're not on the same axis. They're connected though, right? By the body of the tricycle. Yes. And the velocity, that's because they are.
I think that counts.
Yeah.
It does.
I just thought because they went the same way.
Yeah, because if you had it, you could put it on 2 different turns. If you hit a wheelie. Have you put it?
Okay.
And you hit a reverse.
Yes.
The wheels would be going.
But it's more like Daniel said, it's more they're connected through the ground. They're traveling the same distance together.
I'm glad you cleared that up.
Yes, yes, yes. All right. A child can pedal the front wheel at a rate of 40 revolutions per minute. How fast does this make the crazy car go in inches per minute? Okay, so we know that 40 RPMs, right? 40 RPMs. That's our angular velocity. Agreed? Angular velocity is your circle, your rotation. All right. It wants us to find the linear velocity because it wants to know feet per second. All right. In order to do that, our angular velocity has to be in radians per time. Currently, it's in revolutions, right? So I'm going to have to convert from 40 revolutions into radians. How much is 1 revolution? 2 pi. So how many is 40 revolutions? 80 pi. 80 pi radians per minute. So that was the first thing I had to do is I had to have my angular velocity in terms of radians. Is it in terms of it? Yes. Okay. Next, to find my linear. Your linear velocity equals your angular in radians times your radius. Do I know the radius of the big wheel?
Yeah.
I do. What is the radius of the big wheel? It's 10. So therefore, I end up with 80 pi times 10. And what does that give me?
800.
800 pi. And that's just in terms of inches per minute. So I have 800 pi inches per minute. Well, what does it want my answer in?
Inches per minute.
No, it doesn't. What's the final?
It- Feet.
Feet per second. Well, inches per minute and feet per second. So I'm gonna have to convert 800 inches per minute into feet per second. How do I do that?
Train track.
I can set up my train track. So we have 800, I'm gonna do it at the top because I don't have enough room. 800 pi inches over 1 minute. Getting rid of the inches, turn it into feet. 12 inches is 1 foot. And then inches are gone. And 1 minute is
60 seconds.
60 seconds. Am I in the units that it's requested?
Good.
Yes. So I'm multiplying 800 pi times 1, which is just 800 pi. And then I have 12 times 60. What's 12 times 60?
720.
720. All right. So approximately, what is this in feet per second?
Trying to get it to the simplest one.
So we need 800 pi. And we don't have to simplify if we're just finding the approximate.
Oh, 80 pi over 720.
And that gives us
0.11111.
3.49
What?
feet per second. I put the whole thing. To find
I
the,
just put 80, I didn't put
Oh, I was
800,
like,
that's
what?
why.
You told them, you say, yeah.
I said, yeah, to what I was right. Cause I'm like, yeah, 3.49 feet per second. All right, so that kid is pedaling. All right,
Miss Jones, I was talking about these.
Yeah, we knew what
we know what you're talking about.
These
They're-
not called big wheels?
No,
I've always thought it could be.
it's a car. All right, here we go. Stay on track. At this linear speed, what would be the angular velocity of the same wheel? Okay, so we now know the linear speed. And we want to find the little one, right? Because their linear speeds are going to be the same because they're connected by the ground, right? And so because they're connected, on this one, what is its radius?
3.
3. So again, we know linear speed equals angular speed times the radius. So I'm going to plug in what I know. What was our linear speed? 3.49 equals, and we're looking for our angular, and what's our radius?
3.
3. So what do I need to do to find the angular speed?
Divided by 3.
Divide by 3. All right, so how fast is this little car moving? Angular speed equals,
1.16. So 1.2.
I'll put 1.6. And this is in seconds, radius per second.
Yeah, we get.
All right, doable? Yeah, barely. Again, it's all about using the formulas and the fact, knowing whether it's linear or angular.
Period.
All right, this one. What time is it?
4 minutes.
Oh, let's see what happens. On a boat, a sailor must turn a crank that is attached to a spool to reel in or tighten a rope. The crank handle turns with a radius of 16 inches, but the radius of the spool is only 10 inches. Would the crank and handle and the spool have the same angular velocity or linear velocity?
Angular.
It's angular. Why is
Because they're on the
angular?
same axis.
There we go.
Ooh,
Good
Done.
job.
I could do that. That's a test question. Easy.
They're on the same axis, okay? Easy enough?
Mhm.
All right, now it says the rope is being pulled in at a rate of 20 feet per minute. Does this represent linear or angular velocity? First off, what is it? Pulling it in at a 20 feet per second, is that linear or angular? It is linear, so we're just gonna go ahead and circle linear velocity. And so it says find the spool's angular velocity and include the units. All right, so we're gonna use our linear velocity to help us find our angular velocity. How do I do that? What's the relationship between linear and angular? Well, glad you asked. Linear velocity equals the radius times the angular velocity. Okay, and it says that the rope is being pulled at 20 feet per minute. So I know that the linear velocity is 20. So 20 equals, and then we have to find the radius. So what are we describing?
It's the 10.
The 10, because it's the spool, right?
Yeah.
So we're looking at 10 times angular velocity
And we divide by 10, which would equal 2.
equals 2. Two, and this is in, what was our units? Inches,
Inches, yeah.
radians per inches.
Question.
Is it feet?
Well, it says the radius is an inch.
Oh, we didn't, fudge sickles.
So do we,
20 has to be
What?
converted to
Okay.
inches
that's what I was gonna ask.
after we did it.
Sorry,
No, I'm
I
playing.
just noticed that.
I was like, that's not what I wrote in my notes. All right, 20 feet is how many inches?
240.
There we go.
Yeah. Good job.
Good job.
It says it right there.
Oh,
Yeah.
oh, yeah. That's why it's there.
Equals. So therefore, this leads to angular velocity equals what?
24.
24. We're so smart, guys. 24 radians per minute. Because our time is in
I
minutes.
see, I see.
So 24 radians per minute.
Ooh.
And then the last piece I'll leave it up to you to do is determine the angular and linear velocity of the crank handle.
Oh, no, I'll do that.
Okay, remember, because they're connected, they have the same what?
Axis.
They have the same axis, so they have the same angular.
Yeah, angular
Axis,
velocity.
Same axis, angular velocity.
Okay.
Same axis, angular velocity. AA